Half-life calculations. Half-life, remember, is when your reaction has progressed or your concentration has dropped by half the concentration of the original. Okay, and so again, there are formulas for this one. Fairly easy to do. You just need to know whether it's first order or second order. So let's look at the first equation. The decomposition of ethane C2H6 to methyl radicals is first order with K is equal to 5.36 times 10 to the negative 4 per second at 100 degrees centigrade. And then here is our equation. And the question is, what is the half-life of the reaction? Okay, so a very simple question. The equation that you use for half-life for first order reaction is T half is 0.693 over K. That's the equation to use. So which means that T half for us is going to be 0.693 divided by 5.36 times 10 to the negative 4 per second, and this is 1,293 seconds. One of the key things here for the first order reactions that you can see is that the concentration of the reactants are not really involved. T half or half-life of a first order reaction has nothing to do with the concentration. It has everything to do with K, but nothing to do with the concentration of starting materials. All right, next one. Iodine atoms combine in gas phase as I plus I to give I2. The reaction is second order, so now we're calculating the half-life of a second order with K is equal to 7.0 times 10 to the power of 9 molar second per molar second at 23 degrees Celsius. Calculate the half-life when the initial concentration is 0.6 molar and when the initial concentration is 0.42 molar, which means we're actually asked to do two problems here, not just one. So we're calculating the half-life for concentration at 0.6 molar and then concentration at 0.4 molar. Okay, so two calculations to do. Now for a second order reaction, our equation is T half over is equal to 1 over K and A original. Okay, so in this case you can see that we will need the original concentration of the starting material, unlike the first order, which doesn't require the concentration. Okay, we just require the K value, but here we do. Okay, and so let's calculate the half-life for both. So T half at 0.60 molar is equal to 1 over K, and the concentration is, 1 over K. K is 7.0 times 10 to the power of 9 molar second, and then times the original concentration, which is 0.60 molar. Cancels out, and we're left with seconds, and the answer is 2.4 times 10 to the negative 10 seconds. That's our first answer. And then T half at 0.42 molar is going to be, again, the same calculation, 7.0 10 to the power of 9 molar per molar second, and times, now the initial concentration is 0.42. Now without doing detailed calculation, if you can figure out whether the answer is going to be less or more. Okay, so initial concentration here was more. Initial concentration here is less. Okay, and so if the initial concentration is less, then answer should be a little less also. Okay. And the answer is 3.4 times 10 to the negative 10 seconds. Okay, and by less, I meant that it will take longer for this reaction to take place. So the initial rate of reaction is dependent on the concentration. The higher the concentration, the shorter the half-life. Okay, and so here the concentration 0.42 was less than 0.60, so it takes a longer time for the reaction to reach its half-life. Okay, so it goes a little slower when you have less concentration. So it kind of tells you that your rate of reaction is dependent on concentration. The more concentration you have, the faster the reaction is going to go.